Welcome everyone to this episode of Ask an Astronomer. My name is Stefan. I'm a PhD student at the Institute of Astronomy at the University of Cambridge. And we're here to answer all your questions about astronomy, science in general, everything about the universe actually. And you can just ask your questions in the YouTube chat or in the Slido link that's in the description. Or you go just to sli.do and enter the hashtag astronomy to come to the question form. And you can send us questions there without having an account. Also, if you're watching from Twitter, you can click on the link you get to Periscope and can send us questions via Periscope. And today with me I have Eva. Do you want to introduce yourself a bit and say us what you're working on and who you are?
Yeah, hey everyone, I'm Eva and I'm a second year PhD student at the Institute of Astronomy at the University of Cambridge. So my research is mainly observations based, so I'm specifically looking at what we call active galactic nuclei. So these are black holes, supermassive black holes, so very, very, very massive black holes at the center of every galaxy. And when these black holes are feeding, when they're active, they produce a lot of light, and often this light outshines the light produced by the galaxy. So I'm really interested in looking at the relationship between the supermassive black holes and their host galaxies they sit in, and I specifically use a naturally occurring technique called gravitational lensing. So on the screen right now there is we can see a gravitationally lensed image. So gravitational lensing is basically where you have a really distant galaxy, a background object, and in front of it there is a massive galaxy or galaxy cluster, and as the light travels from this background galaxy towards this massive galaxy, the light is then bent towards us and magnified so we can see these objects. And it's really useful because it magnifies the light, we're able to see much fainter objects that we may not be able to see with our telescopes. So yeah, we can get a better understanding of what's going on with these objects.
Great. Okay. So then let's already start with the questions we got. So we just got a question a few minutes before the stream started on Slido, and also on YouTube actually, that gravity is what is called a pulling force, but some astronomers say that it can also push in some extreme conditions, and whether or not that's true. So gravity is actually the only force that can only kind of pull, as you say it. So all the other forces, like electromagnetism and the weak and strong nuclear force, can both kind of pull objects together and push them apart. For example, when you have electromagnetism, when two charges are identical, the objects push away from each other, but if the charges are opposite, they attract each other. But gravity doesn't have any kind of charge. Basically, this means that masses can only be positive. So everything in gravity just pulls together. And so what you say in the YouTube chat is there like a field of particles surrounding Earth? Basically, that's our atmosphere, right? So the atmosphere particles, like all the air molecules, get pulled towards Earth because Earth and the particles are attracting each other. They're pulling on each other via gravity. Yeah, so that's a good question. Thanks for that one. What's the difference between astrophysics and astronomy? Eva, do you want to say something about this?
I can definitely say something about this. So kind of in the olden days, astronomy used to just be like observations and looking at stuff, and astrophysics is the sort of physics behind it and often trying to understand what's going on. Like, say we're looking at a star, we really want to understand what's going on in a star, then you'd be an astrophysicist. Or if you were trying to understand what was going on, if you're just observing it, then you'd be an astronomer. But I feel like these two terms nowadays, if you talk to anyone who is in astronomy, astrophysics, they tend to do a bit of both. So for example, I do observations, but I do the observations so I can really understand the sort of the physics behind what's going on. So we're all astronomers and we're all astrophysicists. It's just these two terms that seem to be kind of separate. I think astrophysics, they tend to think is more theoretical, astronomy is more observational, but at the end of the day, we kind of all do the same thing. We're all trying to really understand what's going on. So there's not really much difference between the two. They just seem to be two separate names that people use sort of intertwined with each other.
I mean, I'm doing officially a PhD in astronomy, and I haven't kind of used the telescope for any like actual research yet. Or all my research is based on kind of simulations and theoretical works. So I can totally agree to what you said. We got a question from Periscope actually. Can AGNs behave like particle accelerators, or at least promote fusion for heavier elements to form?
So this is quite interesting because you can accelerate things, but I don't think you can form things. Yeah, when AGN, when they're active, it's things being sort of pulled towards this black hole and heated up, and it's this heating up of stuff falls into the black hole that we're seeing as light. But we can't. I don't think you could fuse elements per se, but things are definitely being accelerated.
Yeah,
so I think get these beautiful jets of particles being accelerated.
I think we did even once discover a neutrino, right? That was accelerated from an AGN that was far away. So from an active galactic nucleus, I guess. But yeah, as far as I know, these fusions happen only in even hotter or even more extreme environments. So exploding stars or other kinds of explosions. How can I be an astronomer? Slash, what A levels do I need to take to be an astronomer / astrophysicist?
These are great questions.
Go ahead.
So, do you want me to take the A level?
Yeah,
do you want me to take the A level question?
I don't know the system. I'm from Germany.
So, if you want to be an astronomer and you want to study astrophysics, astronomy, or even physics at A level at university, then you want to be considering taking maths and definitely physics, because those two things are very, very important. At the end of the day, physics is just maths, so you really want to have really good math skills. If you can, further maths, but don't worry about that too much. I didn't take further maths and I still turned out okay, and I still can do astronomy. And also a really interesting one is taking chemistry. I know there's a sort of big debate on whether to take chemistry for astronomy, but I find it useful, especially when you're dealing with like fusion stuff and all these reactions going on in the center of stars or in explosions. It's really nice, and especially, I don't know if you guys have been keeping an ear out on the news, but there's been this thing called phosphine that's been discovered in Venus's atmosphere, and having a chemistry sort of background is kind of really useful in understanding all those chemical reactions that are going on in planets and exoplanet atmospheres. So you definitely want physics, you definitely want maths. Chemistry is optional, further maths is optional. But yeah, so if you want to do that, you'd study this A level.
Yeah, I'd also agree, and add maybe kind of what exactly, like if you want to add chemistry, for example, it depends a lot on what your preferences are. Like if you like chemistry, go ahead and take it, and maybe you can use this a lot in astronomy. I mean, I know there are astronomy departments that do kind of astrochemistry and do loads of chemistry. Like most of the people working there actually did kind of study chemistry as opposed to astronomy primarily. While on the other hand, there are people like me that, well, actually I did take a chemistry course at some point, but I never used this knowledge in my work, like barely at all. Or when you want to build radio telescopes, you don't really need to know that much chemistry. So you can, or like when you prefer math, if you like math really a lot, you might want to go in the more theoretical direction. So you just take more math courses, and then your research might also be focused on much more mathematics. So there's a lot of kind of freedom there. How do astronomers determine the effect that dark matter has on gravitational lensing? I think that's one for you.
Okay, so the idea is, I mean, we're looking at the amount of deflection of the light also depends on how massive the object is. But when we're looking at when I say object, I mean the lens. So if we're looking at the image on the screen, then this is the orangey yellowy looking object. So that is an object that is the lensing object that's much closer to us. That's a massive galaxy. So yeah, it's the amount of bending of light. But there's also different ways of being able to discover the dark matter content using gravitational lensing. So it's not like nice lensing like this, it's something called microlensing. So this is the idea that if you have, so in this, we can see the arc here, you have, I think it's 3 or 4 of the same galaxy, the same background galaxy. We're just seeing different reflections of it. So you're able to, but microlensing, you'll get tiny little differences in the light, and you can use that to determine the dark matter content. But I don't know it too much in detail. I just know you use a different type of lensing, and you look at different images of the same object, and you determine sort of like a time delay. And if you know a time delay, then you know the speed of light, you can work out, and you know the distance, you can work out lots of different things.
Yeah. So what you can do is kind of do simulations of the whole thing, like just simulate, if this is a mass distribution, then the light would come bent this way, although I'm not that sure how kind of difficult those simulations are. Okay, so we got more maybe one of the follow-up questions to the kind of career advice part. What universities are best for astronomy or physics?
Ooh,
I think that's a difficult question. I think it depends.
I think lots of different.
Yeah, I mean, it depends, of course, on the particular subfield. I think, in particular, for example, in astronomy, there are lots of subfields. You could study the evolution of stars. You could study how galaxies behave, or cosmology on the really large scales. And I think, like, a university might not be good in all of those, but might have really good researchers and really good groups in one of those. So that depends a lot on your focus. Do you want to say something, Gerald?
Yeah, I was going to add to that. So I think with astrophysics, not all universities will offer like a straight astrophysics course. Some may offer a physics with astronomy course, or physics and astronomy course, where you kind of do a bit of physics and a bit of astronomy. And I think at the end of the day, like I personally studied an astrophysics course and I enjoyed it. And then I had a common first year of my degree with the physics students, so we all got taught the same thing before we specialized. So it just depends on what you want to do. And again, yeah, look at I suppose it doesn't really matter too much for undergraduate. Look at the research groups that are there at the university, kind of what they specialize in, because they will put a slight focus on that in the teaching, but you will get a general background to astronomy and astrophysics in your degree, so you don't have to worry about that. But some universities might add like little extra courses. So I think in my university, they offered like an astrobiology little section because they had astrobiologists. Like they will teach those sort of specialized subjects, but you will kind of get a general astrophysics background no matter where you go or what you decide to do.
Okay.
And then you can focus on it if you want to pursue that further.
We got a question a few seconds ago. A few minutes ago, I guess. Well, what exactly is a graviton? So I can say a bit about this. So when we talk about kind of the forces in the universe, we have gravity, we have the electromagnetism, we have the strong and weak nuclear force. And over the time, people figured out that most of these forces, well, at least we know it for the electromagnetic force and the strong and weak nuclear force, are kind of interact via actually small particles. So there are particles, the photons are the particles that transmit the electromagnetic force, and there are bosons. I think it's the the Z boson, and what was the other one? W, right? W boson that transmit the nuclear forces. I think the weak nuclear force, right, and the strong one, the gluons. Anyway, these particles that transmit those forces. And it would be kind of a logical assumption to maybe think that gravity also has a particle that transmits the force, that is like responsible for the force kind of interacting between two objects. But we have not found this particle in any way. So for example, for the weak nuclear force at the Large Hadron Collider, if we collide particles at the right energy, we produce a lot of those particles, of those Z bosons or W bosons that are responsible for this force. So we can actually make them in the lab. But we have not any indication of kind of a gravity on how massive it is, what properties it would have. So it's kind of a hypothetical particle that transmits gravity, but we haven't found it yet, and we don't know if it actually exists or if there's some other mechanism of how gravity works. So it's more like a theoretical idea. How are we able to see a neutron star? Oh, do you know that?
So what we're tend to see, because neutron stars are very, very small, so kind of to explain the background, a neutron star, so say a star more massive than our sun, after it goes supernova, it will leave behind its core, which will be a very tiny, compact object. So they're about the size of the M25, so they're about the size of London, these things. They're very, very, very small in diameter, but these are very, 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 very dense objects. They're made of neutrons, and these things can't collapse down any further. Say if it was a more massive star, I think it's like above 10 solar masses, then you tend to get a black hole afterwards. But a neutron star, so this is sort of the remnant after a massive star has gone supernova. These very, very dense, and sometimes quite a lot of these times, these neutron stars are spinning. And what's happening is, as they're spinning, they're also producing these jets of radio emission. And if they're at the right orientation, you can actually observe these radio jets from Earth, and you can see them. So every few seconds, you'll hear you see like a little blip going around as this neutron star the jets from these neutron stars sweeping around the Earth. So you can see them using radio waves.
And when we're talking about this, we got a question on Periscope. Can we differentiate between subluminal relativistic jets from AGN and Hawking radiation? And if so, how? So I think there's a lot to explain here in this question. Do you want to go on with this?
Okay, because I could start with what Hawking radiation is. So Hawking radiation is this idea that you have two particles that are produced near a black hole, so they spontaneously produce, and what happens is they usually annihilate and disappear again. So you can have like an electron and a positron, which is just a positively charged electron. Then they annihilate and they become nothing again. But the idea is if these two pair of particles is produced near a black hole, then one would fall into a black hole and the other wouldn't, and you'd still get that particle basically existing. And the idea is this. The idea is you'd still see this particle, but Hawking radiation is very, 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 very faint, and you don't get to see that. It's not very bright at all. So you wouldn't normally see this because, again, like we talked about, the AGN, the light from the AGN outshines the galaxy. So, but I don't know about subluminal relativistic jets.
Yes, I think the part with the jet is basically when you have like an AGN's jet pointed towards Earth or towards our general direction, you would see it very bright, right? That's what people call a blazar, which is just a AGN that has its jet pointed towards us. I think it has this particular spectrum, like it might have some synchrotron part. I'm not sure about the exact properties, but I think we know pretty much what the spectrum should look like. And we also know pretty much
It'd be a lot of narrow lines.
Okay. Okay, yeah. Well, and for Hawking radiation, I think we also know the spectrum. And I think it's not the same. But even if it would be, Hawking radiation is so much weaker. So you won't have any chance of detecting Hawking radiation from this distance. You would have to get much, much closer to the black hole. I don't think there's any even futuristic kind of way of detecting Hawking radiation. Like I think there's no plans for an experiment to get this. So yeah, I guess that's a way how you can differentiate, or well, find out that anything you see can't be Hawking radiation. Yeah, I think if you would notice, oh, the spectrum looks like Hawking radiation, maybe you would find out, oh, well, maybe it's stronger than expected. That would be really cool. But I don't like we didn't find anything. So yeah. So a follow up on the force question from before. The question reads: forces like gravitational force, magnetic force, etc., are just movement of particles which is attracted to a particular element, which interact with particles that surround the element. So it's one thing there is how we describe things mathematically and how they really are is not necessarily related. So the way we kind of mathematically describe interactions between particles is basically we kind of draw lines and say, oh, a particle goes along here, like a gluon goes this path and a W boson this path. But that's not necessarily what happens. It's just kind of a way to make our computations easy. And in our mathematical framework, we just say, okay, all space is what is kind of filled with what we say is a field, and actually many fields. And each of those fields corresponds to one particle. So let's say you have an electron field everywhere. And then this field is excited everywhere where actually there is an electron. So basically you could just say, oh, there are electrons. But if you're a mathematician or theoretical physicist, you would say, oh, there is a field and it's excited at some points. And I guess you kind of could describe it that way, but I'm not sure like that the way you describe that is necessarily like correct in that way. I'm also not sure if I understand it completely correctly. Yeah, I mean, if you want to clarify on that, please feel free to do so. We just talked about neutron stars, and we got the question, why do neutron stars emit gamma ray bursts? Do you know that?
I don't think neutron stars do emit gamma ray bursts, but I could be wrong.
Okay, what objects do create gamma ray bursts? Is it just
gamma
kind of
bursts.
Is it like like mergers or something?
Maybe, but I'm not entirely sure.
Okay, yeah. I don't think like a normal neutron star would create a gamma ray burst, because then we would get tons of gamma ray bursts. And I don't think we know of any repeating gamma ray bursts, which would happen if neutron stars would just produce them. So I think it might be mergers of neutron stars that do produce them. Yeah, I think wasn't that with the the gravitational wave detection of the merging neutron stars, we had an optical counterpart, right? And I think that was a gamma ray bursts. So
Okay.
I think, I'm not sure if we know all the sources of gamma ray bursts or if there are like some that we know. But neutron star mergers could be one, but I'm not sure in this area. So might be, but we're not sure. Oh, we got another question. I'm 13 and I want to be an astronomer. How much should I know? Because I do not want to be behind everybody else when I get to A-levels or university.
I was going to say, don't worry. You'll be caught up. Like, everyone's in the same place. I think there's too much pressure on people doing like a lot of work outside school enough. And school's stressful enough. You've got lots to do as it is. You will be prepared for university, whatever course you want to do. So you don't have to worry about doing all that extra work. Just focus on, doing your schoolwork, passing your exams, and enjoying school as well. So yeah, you will be caught up. There's no panic about being behind.
Yeah, also don't worry too much about kind of finding everything about your kind of future goal, like future PhD topic in advance. Like, I didn't know that much about astronomy before I started my PhD. And I know many people whose PhD topic is not necessarily that much related to what they did before kind of in their bachelor's. So don't worry too much, as if I said. Like, especially because you're 13, you're still in school. Don't worry. You'll have time. We got one question, what is strange matter? And I feel we get this question a lot, but I never heard the word strange matter. So I always think it might be related to the kind of the strange quark. But maybe if you want to clarify, there was an answer. Strange matter is a matter which consists of strange quarks. Yeah, that sounds about what I would expect. Okay, so let me explain what a strange quark is then. And also let me go to the fitting slide here. So in our model of particle physics, we think that everything in the world is made up of these particles plus gravity. So these particles are, basically everything that makes up. So the left part, so all the 12 particles on the left, are all the kind of matter. So those are electrons, those are protons, neutrons, atoms, tables. Everything is made up of these things. And on the right side, you get the forces. So the gluon, which does the strong force, Z and W bosons for the weak force, and the photon for the electromagnetic force. And also the Higgs for a bit of massless shenanigans. And gravity is missing. As I mentioned before, we don't know how gravity works exactly on the kind of particle physics level. And normal matter, so most of our bodies, most of our tables and our houses are made up of only 3 of those. Only the up and down quark and electrons. Basically, when you take 1 up and 2 down quarks, is that right? Yeah. You get a neutron, and if you take 2 up quarks and 1 down quark, you get a proton. That's all you need to make atom cores. And then you add a few electrons, and you can make atoms. There you have hydrogen, helium, and everything else. What you can do, though, in a particle collider like CERN, you can smash stuff together and try to make more special atoms. So, for example, you could try to smash a down quark with a few. Actually, I'm not sure what exactly you have to smash together. I'm not a particle physicist. But you somehow can produce strange quark. And then when those strange quarks, let's say you have a strange quark plus an up, let's say 1 strange quark and 2 up quarks, you get a particle which is similar to a proton, but a bit different because it has a strange particle in it. So it's a lot heavier, but has the same charge and behaves slightly different. Actually, I forgot the name. I think they have like fancy names, all those particles. And you can see from this large table, you can make lots of combinations and lots of interesting names. And strange matter is, I guess, everything that just contains 1 strange quark. Yeah. What are quarks made of? Good follow-up questions. We don't know. Maybe they are just kind of fundamental particles, like there's nothing beyond quarks. Maybe they are actually made up of strings, according to string theory. We don't know. So far, every time humans thought, oh, that's the most smallest thing we can get, and there's nothing beyond, we always found something. So I'm not that confident in quarks being the last thing. But we have no hints of quarks being made up of something. Okay, so imagine if we are able to understand these particles, those which I mentioned above, we were able to determine how will a body interact in a particular field of force. I mean, that's what we can already do with kind of normal classical fields, right? When you say you have an electromagnetic field that has a certain strength, and we can put an electron in there, our equation selects exactly it will get accelerated with this force, which is, I think, just field strength times charge, and then we get how it works. Yeah. Oh, we just mentioned jets in the previous answer. We got a question about what are astrophysical jets. Do you want to explain this a bit, Eva?
So I know about relativistic jets, so you kind of talk about astrophysical jets.
Oh,
and
okay.
relativistic jets.
Sorry.
So no, I just saw the question earlier. So relativistic jets are basically these jets produce, well, there's a lot of particles that are relativistic, which means these particles are traveling very, very close to the speed of light. And astrophysical jets, I presume, are not traveling at the speed of light or near the speed of light.
Yeah, well, I guess, yeah, it might be just a general, like, relativistic jet is probably just a sub-classification of astrophysical jets. Yeah. So how do you know how the jets in general kind of created?
And it's to do with conserving angular momentum. So if you've got your thingy spinning, then to conserve angular momentum, you launch these jets. But I'm not too...
yeah, we have a pretty picture of a jet, but I'm also not an expert on this topic. So maybe, yeah, like I can give the explanation that I have been given by like people working on this topic. So basically, it has to do. Well, I can't give you the exact explanation. I'm working on cosmology. I don't know how a jet works, but the basic idea is that you have lots of magnetic fields, and in some way, via the fast rotation, they're like the field lines can't kind of hold in the way they're supposed to hold, and like, okay, that's okay. Yeah. No, I try not to say anything wrong here, so I better say nothing. You get just, basically what happens is that you get bursts of particles or energy, or, well, both usually, that are going out perpendicular to the plane where something is rotating. So when you have a black hole, it usually forms a disk around it where material is rotating and falling to the black hole. And perpendicular to the disk, you get really fast moving streams of energy and particle, which we call jets. But how exactly this works, we can't tell you today. But if you come back in 2 weeks, you might find someone who is an expert on this field. I should check that. Okay. Please explain nuclear pasta. I'm not aware of nuclear pasta, but if you want to clarify that, I might be able to explain it. What are quarks? Maybe I just had that. What is quantum loop theory? Sorry, I did hear of quantum loop theory someday, but I have no idea what it is. I guess, Eva, you don't know either. Okay.
Nope.
No, sorry. I wouldn't be able to say anything correct, so let's not say anything better. We got a question earlier that I actually skipped, so let's get back to that. I wrote it down. Quantum cosmology. So what is quantum cosmology? So cosmology in general is kind of the study of, the universe, how it evolved, how it began, and quantum cosmology is, I guess, the part of that needs quantum physics. So that's usually the very beginning of the universe, when everything was really small, and quantum effects played a big role. And one big kind of area in quantum inflation is quantum cosmology is inflation. So that's the part that is at the very beginning of the universe, when it expanded really, really fast. And during this expansion, quantum effects like the quantum fluctuations actually had a real effect, because those quantum fluctuations would expand with the space, or space would kind of expand at different speeds where those fluctuations were, and this created today's structure to some part. Like basically large galaxy clusters are in some way seeded by those quantum fluctuations. And what you could call quantum cosmology would be kind of finding out how exactly this worked, and how various quantum physics models, for example inflation models, would affect today's universe, and if they could be true or if they would be ruled out by observations, things like that. Yeah, why is planet Haumea shaped like an egg? Oh, do you know that planet? I haven't heard.
Dwarf planets. It's in our solar system, but I can't remember if it's a dwarf planet or asteroid.
Well, it's certainly not a real planet, so it's probably a dwarf planet.
I think it's it's not one of the big planets. It's one of the smaller dwarf planets, and it's probably because I think it lives in the Kuiper belt. I could be wrong. So if anybody knows this, please correct me. But its gravity isn't that strong, and it's interacting with lots of other objects in its path. So if it's in the Kuiper belt, then there's lots of other large bodies that could like crash into it and stuff like that. So altering its
yeah,
appearance.
I think like basically, so how do planets get circular? They get circular by self-gravity, right?
Mm-hmm.
So basically when you have, let's imagine you have a really huge egg-shaped planet, then the edges of that egg would have a stronger gravitational force because they would be kind of along the axis. So they would be pulled towards the planet, while the parts that are close wouldn't have such a force. And if the planet is large enough and its gravity is strong enough, it would shape itself towards a sphere. So basically, I guess all planets more or less started as some weird shape, but if the gravity wasn't strong enough, they just stick to that shape. And that might be why this dwarf planet slash asteroid slash, we're not sure what exactly it is not shaped like a sphere, but like an egg. That's also the reason why asteroids look like, clumps of rocks instead of nice spheres, because they're not heavy enough to make themselves into a nice sphere, which is what planets and stars do. What is the probability that the Big Bang occurred? Oh, that's, well, I mean, that's a difficult question, and it depends on what you mean by Big Bang. So if you mean, kind of the beginning of the universe in general, well, I mean, we're here, so it's probably kind of some kind of Big Bang. Actually, so there was a discussion back in the days when the Big Bang was still new, where people discussed whether or not the universe was created in the Big Bang, or it had always been there and kind of always, hasn't started at some point. And basically, we did kind of observations, and we found out mostly due to the cosmic microwave background, which is pretty directly kind of an echo of the Big Bang. It was pretty clear that the Big Bang actually happened. Of course, then afterwards, people can come up with theories that also produce cosmic microwave background, but do not require a Big Bang. And in particular, how exactly the Big Bang happened. So did it happen via this one particular model? Did it happen with inflation? Did it happen in some other way? That's something we're not that sure of. So Big Bang is the simplest model that still fits all our data. So that's kind of the reason why we think it's true. Like that worked out quite well in the past. Just go for the simplest model that fits your data. But of course, we can never prove a theory. Like Newton's gravity was working really well. At some point, people noticed, oh, yeah, it doesn't explain this part, so it must be wrong. It doesn't explain Mercury. It doesn't explain shifting of stars. And then people had to switch kind of to the Einstein's theory of gravity. And the same could happen to our Big Bang model. If we find something that doesn't work with the Big Bang model, we have to revise our model. But for now, it's kind of the simplest model, and it seems to be true. But yeah, we can't prove it, or we can't say it's 100% that it's happened.
Mm-hmm.
Oh, we got a lot of new questions. Where do we start? Up there. How do we measure magnetic field of a celestial body? So I think for planets, we can send spacecraft there. And I think that's the main way to measure them. Or is there another way?
I think so.
I could imagine we might be able to detect an aurora in other planets, although I'm not sure if we can do that.
We can detect the aurora in Saturn.
Oh, okay.
Jupiter. You can see it. You can see it. So I presume you must be able to measure.
Okay, then that's
something.
Probably a way to measure the magnetic field. I guess something similar might work for the Sun. But otherwise, you can, for example, for the interstellar space, we have the Voyager spacecraft that is kind of flying since actually lots of years. How many is it now? Certainly. Yeah, okay, I don't even know when they launched. But they have.
It was launched in the 70s, wasn't it?
Yeah, it was really long ago. Anyway, they do have lots of measurement devices on board, and I think they also have one for magnetic field. I'm not 100% sure, but those spacecraft can, of course, measure the magnetic field everywhere they go. For the kind of galaxy and everything we can't really directly reach, there are also methods to kind of measure or at least estimate the field. Although I'm not familiar with the exact details of those methods. So yeah, for that you might have to ask someone else someday. That's not me.
Magnetic fields are really complicated.
Yeah, I notice a trend here. Okay, do you know that these particular galaxies contain these particular stars? Oh, that's a cool question. Do you want to talk about this, or should I? How can we find out what stars kind of like where in what galaxy is the star? Like, is it that the galaxy is in a particular galaxy? I'm not sure if I interpret the question correctly.
Or is it asking how can you tell kind of what type of stars are in certain galaxies?
Okay, I mean, maybe we just answer that question.
We can answer both.
Yeah, go ahead.
Go on. I was gonna say, if you want to kind of understand what kind of stars there are in galaxies, then all we have to do is look at the color of the galaxies. So if we can scroll back to my gravitational lensing image, we have two colors we can see. So we have that orange central massive galaxy, and that has a red color. And then the ring, the Einstein ring we can see, which is the background galaxy being lensed, it's got a blue color to it. And the yellow color comes from the fact that there are much older stars in these galaxies. So all the these are a lot smaller stars, so stars like our sun, these live a long time, whereas in the bluer galaxy, it's still forming stars. There's a lot of blue stars. So these blue stars are much hotter stars. These are much bigger stars. But these bigger stars use up all their resources much quicker, so they die a lot sooner. Whereas you won't see many blue stars in really sort of old galaxies. So that's one way of determining kind of what type of stars, but go on.
Yeah, I just got, there was just the follow-up that what was it, the number of stars in the galaxy. So how can we determine how many stars there are in a galaxy? Also, for the audience in general, we have about 10 to 20 second delay between us seeing your questions and you writing the questions. So don't worry if we don't see your answer within like 10 seconds. So do you know how we find out how many stars are in a galaxy? I guess we can just like measure its brightness, right? So we know kind of how bright the average star is, or we know the kind of the distribution of how many bright and less bright stars there are. So by measuring kind of what type of galaxy is, I guess, is also useful, and then what brightness it has in total. We can basically just divide the brightness by the average brightness with a few caveats and get the number of stars. Oh, we got a lot of questions. So there was one question about an object falling down, like say out of a plane, and whether or not like how the mass behaves there. And one thing to keep in mind is when objects falling down, their speed doesn't depend in any way on their mass, right? Like assuming you don't have any air resistance or something, a feather would fall as fast as a stone would, in vacuum at least. And then the other part is, I guess, about kind of relativity and how if the mass increases. So in general, if you would have, like, let's say you are, in the vacuum and you have an object and you move it fast, then it seems to have a higher mass. Like, that's a kind of simplified approach, but objects that move seem to have a higher mass than objects that are not moving. That's also the reason why we can't get anything to the speed of light, because they would get heavier and heavier in that way. Although on the example that you described, where you say you drop something out of a plane, it's complicated because special relativity doesn't describe accelerating objects, so it's very hard to calculate this. But on the other hand, actually objects in free fall are, I think, quite easy to describe, because they're just an object in free fall is just as an object in vacuum. So the mass of that object, the one that you throw out of the plane, assuming there's no air resistance, would just behave as it would be standing still in the vacuum somewhere. So it would be actually lighter than it was while you were flying on the plane. I think that's right, yeah. Oh, there are lots of questions. Oh yeah, oh dear. So we got one about, let's start at the top here. Astrology is not a science. Astronomy is one. Maybe that doesn't answer that question. Yeah, astronomy is a science of finding out what happens in the universe and with stars. Astrology is just some, yeah.
It measures like positions of stars and where things are in the sky, and depending on what planets are up, and then it kind of predicts.
I mean, it claims to predict, but I mean,
yeah.
Yeah, there's no scientific evidence for astrology actually working, so I'm not very convinced. How are you sure that Einstein's theory of gravity is true? Are there any other theories on this? There are indeed other theories of gravity. There's one famous or infamous one called MOND, Modified Newtonian Gravity Dynamics. which is kind of an alternative. So as I said before, we can never prove a theory is true. We can just say, okay, it works so far, it's a simple theory, but we can never say it must be true. There could always be, someday we find an object that doesn't work with that model, and we have to update our model. And the question. So for now, Einstein's theory of gravity is a really simple theory compared to alternatives, and it explains everything we see. Like, it explains dark matter, it explains the universe. Like, some caveats, there are some small, some problems with, say, gravity rotation curves, but mostly Einstein's gravity plus the existence of dark matter explains things. One of the alternatives is the modified Newtonian dynamics theory I mentioned. It is kind of an adjusted version of Newton's theory that does explain gravitational rotation curves without the need of dark matter. So basically those people were like, this dark matter idea sounds a bit suspicious. Can we get the same result without dark matter, but just by modifying our gravity's laws a bit? And they kind of got some success. They can't explain everything yet, so that's why Einstein's theory is still the kind of preferred one. But we might be able to find an alternative, and maybe that works better or is simpler than our current theory. But for now, we think it's probably true. It's a kind of most likely theory that we have. Why does the Earth spin? That's a nice question. Do you want to answer that, or should I talk about it?
You should answer this.
Okay.
Just trying to keep up with the questions.
Oh, I'm totally lost with the questions. There are far too many questions. So when you form planets, so what happens basically is when a star forms, you kind of have a lot of gas or a lot of material that's left over. Like in the middle, you form a star, and all the other material forms kind of a disk around the star. And out of this disk, all this kind of rotating material forms a planet. But because all this material is spinning, the conservation of angular momentum, like a law of physics, says basically that kind of the spin, like spinniness, like the amount of spinning around you have, has to be conserved. So that basically leads to the planets themselves also spinning around. Like, it's just, they were spinning at the beginning and nothing stopped them from spinning. Like, the material was spinning, now it's still spinning. And that's what's made the planet spin initially, and they're just still going on. I think they're actually slowing down, like, really, really small amount. But I don't think, like, it's not, no, don't worry, Earth is not stopping rotating anytime soon. But yeah. Oh, why is the Earth tilted? Oh, that's an interesting question. Yeah, and it's also really complicated. I'm not exactly sure about that. So, do you know that? Why the Earth?
I think it's to do with. From what I know, I think it's to do when the moon, or when this other thing. So there's a kind of theory that another sort of Earth-sized object crashed into the Earth, knocked a chunk of the Earth out, and that chunk became the moon. And I think it's when it's to do with that, when it got knocked off its axis slightly.
Okay. Yeah, I'm just trying to write down questions here. So we got one question. What is the biggest galaxy we know? Oh, do you know that? I'm not an expert in galaxies.
Oh, I don't know.
Okay.
The biggest galaxy, but these things are massive. So the biggest types of galaxies are what we call elliptical galaxies. And these tend to exist after two spiral galaxies have sort of come together and merged together, so they sort of get loads and loads of mass combined from all their stars. So you tend to get those at like 10 to the 12, 10 to the 13 solar masses.
Yeah, I don't know the exact number, but also basically like the way galaxies kind of grow is basically through kind of mergers, or most galaxies became as big as they are through merging with other galaxies. So basically the ones that are at the top of this merger tree, like that have the most other galaxies merged into them, are the most heaviest ones. They can be really, really heavy, like much heavier than our galaxy, I think. But I don't know the number either. Okay. What was the next one? How are bosons formed? Basically, basically every time you have enough energy in some small enough space, you can form bosons. Like, that's what people do at CERN, and that's why particle colliders work. You just smash simple particles together, have enough energy, and you can just produce everything. Like, that's what LHC does. It just takes two protons at together 14 tera-electron volt, that's an energy, and smashes them together, and they produce all kinds of particles that are below this energy. So that's actually quite nice. The detailed calculations for this are much more involved, and I couldn't do them like right now. Are there many types of space, like interstellar space? Do you want to say about this?
One.
Like, what's the difference?
Okay, so it's space is space. Well, we say interstellar space, so that is the space between stars. So inter, the in-between region, and stellar is stars. And then you have like intergalactic space, which is the space between galaxies. So it's all the same space. We're just kind of deciding what specific area of space we're looking at. So we say interstellar space, we're looking at space between stars, looking at intergalactic space, space between galaxies. But it's all the same space. It just depends on what area.
Okay, so we got another question. I'm just scrolling down the list about flavor. So the flavor of particles. So basically, I showed you the kind of table before, and we have these normal particles, up, down, quarks, electrons, and then we have the second row, which is strange and charm quarks, and then we have the top and bottom quark on the very right. And this is what we call flavors. And the reason is that to convert, like you cannot just convert from an up quark into a, say, charm quark. You need to have some interactions with other particles. And the reason for this is a conservation of what we call a quantum number. So basically, they have a certain category, and you can't just convert from one category in the other. And because we like nice names, we call that kind of category flavor. So that's just how we call these categories. And yeah, they're kind of basically 3 flavors in that sense in the standard model. How do we know about the Oort cloud? Do you know that? I guess the Oort
cloud is the sort of, the Oort cloud is this region, or this cloud around the solar system of, I think it's asteroids and comets. And every so often these comets come into the solar system. So, they talk about this thing that, oh, we've seen this comet or asteroid that's come in, and it's come in from like a long distance. So it doesn't exist within the solar system, it kind of exists around the solar system. And you can figure out if it's there or not if you trace sort of the orbits of these objects. So we just have the objects and you can like trace it back and see.
We got one cool question from YouTube. When will Earth, like, what about the core of Earth and how does it cool down? Or when will it cool down? And how hot other rocky planets' cores are? And that's, I think, an interesting question. So I think it took quite a while for Earth to kind of cool down from, volcanoes, basically made of lava, into something you can live on. Basically, it took billions of years, so it will take certainly a very long time for it to cool down. And I do think that before, like, the sun will burn out before Earth will cool out. So I think we don't have to worry about Earth cooling down. And do we know anything about the kind of temperatures of exoplanets? Like, if there are any really, like...
You can measure the temperatures of exoplanets, but...
I guess, like, we can measure the atmosphere temperature, right?
Yeah,
so...
I think it's much more difficult to measure the cores.
Yeah, I'm not aware of any measurements of kind of the core temperature. I guess the temperature of basically any planet is determined by, well, any planet that is close to a sun is determined by the radiation from the sun, right? The Earth atmosphere is like, 20 degrees around, out of my window, Celsius. But that's not because of the Earth's core is heating it, but that's just because the sun has heated it. So that's the same for Mercury, for Venus, for Mars, and most planets for that matter. So it's really hard to measure the core temperature because the temperature we measure is just dominated by the influence from the star. Yeah, so I'm not sure. I don't think we know about exoplanets. What's going on with them? Okay, lots of discussion going on in the chat about the collision of Earth with the exoplanet. So that's very nice. How do we know that there is 74% dark energy? So when we came up with our cosmological model and kind of measured for the first time the energy content of the universe today, we found out that about 5% of it is just the normal matter. You and I, the planets, the stars, the gas. Then about 25% of it were also some kind of matter, but matter we couldn't see. It's what we call dark matter. And then we found, okay, that's 30%. But we know there's like 100% in total. Like we measure more energy than just dark matter and matter. And the remaining kind of leftover part we called dark energy, because it's energy and we can't figure out where it comes from. How do we know this? Yeah, basically what we can do is we use our physical model, so mostly the Friedmann equations, to figure out how fast does the universe expand at different times, depending on what matter it has. And the characteristic thing is matter makes the universe expand in a different way than energy. And we figured out that by the way it expands, that there must be like 70-something% dark energy in the universe. And since it's not normal energy, it must be this dark energy. So that's kind of how we found it out. We didn't directly measure it. And by the way, the effect of this dark energy, by which we found it, is the expansion of the universe. So if you have dark energy in particular in the universe, so energy and dark energy are not the same really, they just have a similar name. And dark energy, or other people might call it the cosmological constant, make the universe expand faster and faster, like it makes its expansion accelerate, which is kind of the characteristic sign of it. And that's what we only found out at some point in the 90s. So it took us quite a while to figure this out. Could you explain how supermassive black holes are formed? Do you know that, Eva?
This is a really hot sort of topic in my field of astronomy, and we don't actually know how they're formed. We think there's kind of different ways we think it could have formed. So it could be like a solar mass black hole. So this is when these really massive stars reach the end of their lives. The pressure is so great and these explosions are incredible that you don't even get a neutron star. It basically just pulls everything down to a black hole, and they think they could have been built up to they could start like that and then build up by merging. But we see really massive, supermassive black holes kind of really early in the universe. So there's a lot of debate of like where these have come from. Have they come from mergers? Have they just like spontaneously appeared? Like, we don't know, and it's still, there's a lot of research needs to go on to how they actually form. But we know how they get bigger and bigger, which is great. But where they actually come from is still a mystery. Whereas like your sort of solar mass black holes, we know they come from big stars that explode. And
yeah.
So yeah. Okay.
One more question was, how do we know the number of baryons in the universe? So let me just explain what baryons. Well, we astronomers mean with baryons basically all the matter that is not dark matter and dark energy. Actual particle physicists would differentiate there more, but we just say baryons. We just call everything that's technically wrong, but we just go with it anyway. So all the atoms, all the electrons, all the neutrinos, all the gas, all the stars are baryons. And one way to measure this is kind of use the kind of cosmology approach and calculate, okay, how the universe is this old. We see the Big Bang in some particular way, and for this to work, we need a certain amount of baryons in the universe. So one effect, for example, is in the very early universe, we had no atoms, right? And at some point we started forming hydrogen. We started forming atom cores. So first we had just protons, and then some of those protons fused with neutrons together to the deuterium, and some of these to helium. And this happened within a few minutes. And we know that deuterium on neutrons. Neutrons decay over after a few hundred seconds. So we can actually measure precisely the time how long this process took based on the amount of neutrons there are in the universe today. And we know the amount of minutes it took basically, and this tells us how many baryons there are. Because if there are more baryons, the fusion works faster. If there are less baryons, the fusion works slower. So you can work out pretty exactly what that is, or at least what the ratio kind of is of baryons to matter or something like this. I'm not sure of the details, but we can get some measure from there. Then additionally, we can see the cosmic microwave background and see kind of the exact patterns in there, and they tell us about how physics worked in the early universe. So how fast did rays propagate, how massive were kind of the gravitational wells, and that again gives us information, how much matter was there, how much baryonic matter, etc. So that's one way to find that out. The other way is to measure it more or less directly, and there was a recent paper this year actually that used fast radio bursts to measure the amount of actually electrons that are in the space kind of around us. And that was quite an interesting result when we found out that they're we found the missing one. So back kind of a few years ago, we did the calculation with cosmology, found, oh, there must be this many. Then, our astronomy friends looked out and said, well, we only see half of them. But now with these fast radio bursts, we found out that the other ones are kind of diluted everywhere, and that's why they were so hard to see. Okay, so we got one. Right, is there any way that black holes will affect humans in our lifetime? That's a simple answer. Do you want to explain why?
I mean, the closest supermassive black hole to us is at the center of the Milky Way, and we live on one of the spiral arms of the Milky Way. So this thing is about 7 kiloparsecs away from us, and only really influences the sort of really central regions of the galaxy. And if one of the big stars around us decided to go supernova, we'd see it, but we wouldn't really be affected by the black hole either. Like, we think when we see these pictures, we see these stars so close together, but in reality these things are so incredibly far apart from each other that we just won't feel the effects at all. So we don't have to worry about that, which is nice.
Yeah, it is. I mean, it also means we will never get to see Hawking radiations, probably. But I guess that's a thing I can live with for not being swallowed by a black hole.
Yeah. I'd like to not be swallowed by a black hole.
We got the question when the first atoms were created, or how they were created. So, now I have to see if I can get the time right. Yeah, the time was about 380,000 years after the Big Bang. So basically the universe started in a really hot state. Like, it was really hot and expanding, and no atoms could form, because as soon as an atom formed, like a random photon flying around would just shatter the atom into parts again. So it took until 380,000 years after the Big Bang, where the universe was continually cooling and cooling and cooling. And then it was cold enough so that an atom could form and not immediately get destroyed again. So kind of the rate of atoms forming was higher than the rate of atoms getting destroyed. And we started forming hydrogen atom and helium atoms. So that already happened after all the nucleus formation. So all the hydrogen and helium nuclei were already there, but just the electrons were, like before, the electrons just flew around through space and didn't stick to a particular core. And then at this time, they started to kind of stick to the cores, and over the time space of a few thousand years, the universe turned from kind of a hot mess of electrons flying everywhere to a cool gas of electrons all sticking where they belong, to the atoms. Yeah. There were a few questions about kind of how we are all made of stardust and what that means, or how atoms get, like, okay, so I just explained how atoms get produced, but of course this was just how hydrogen and helium get produced. Everything else, like in meaningful quantities, does not come from the Big Bang, but from stars, which is why people say we are all stardust. Eva, do you want to explain this? You look like you want to.
Yeah, I love this one. I love this. This is one of my favorite space facts ever. So inside of stars, for stars to be able to exist, basically, they fuse hydrogen into helium, and then they fuse helium and further elements. They produce all the way up to iron, and iron is the most stable element, because beyond that you have to put energy in to be able to break them apart, whereas stars just want to be able to throw some stuff together and get energy out to be able to live. So again, when these massive stars go supernova, what they do is they blow away, they just explode. Their outer layers just completely go mad, explode, and this pushes all those elements into space, basically, because otherwise they're just contained in these stars. And there's also so much energy in these supernova explosions that heavier elements are then produced as well. So they're also fused together. So these supernova explosions, they either trigger more star formation, and this dust and gas gets produced, and more stars are basically produced. So the universe likes to recycle. So yeah, and everything you find here on Earth was produced in stars, because that's how we got it in the first place. So yeah, we're all stardust.
That's really nice. We got 1 minute left. Well, half a minute left. So one final question, and it was about stars appearing large and versus stars being large, and how can we know about the size of a star, or how the brightness and the size are related? Do you want to say a bit about that?
The size of the star.
Yeah, actually, I scrolled past the question already. I just wrote down sizes of what was it? Yeah. Okay, so I think, yeah, why? So sizes of stars. Maybe let's start with this one. Basically, a star is kind of well, it just the bunch of gas kind of gravitationally collapses, so gravity pulls it together, and then in the center, it's so dense that fusion starts. So like mostly hydrogen fuses into helium and creates a lot of energy, lots of photons that want to get out. And then these kind of photons flying outwards push against the material that wants to fall into gravity and stabilizes at some size. And then, depending on what kind of star you have and what mass, the size of the star changes. Do you know how exactly it works, Eva? Because I'm not sure about the sign and the relations exactly. Our massive stars are the larger ones, right?
Yes.
Okay. So
in main sequence, the massive stars are the larger ones, and they come off the main sequence. Then you've got more problems.
Okay. So we'll
just talk about normal happy stars.
Okay. So for normal happy stars, i.e., stars that are not kind of shortly before dying, the larger ones will be the heavier ones and also the brighter ones. So the brighter star, the heavier it is. Basically, you can. I think there's quite a nice relation. You can, from the brightness, you can kind of more or less get the mass and the size of the star by kind of just solving the equations. It's just physics going on in the star, and you can figure out how bright it is. Actually, I think you can also, like, from the color, you can get how hot it is. So that's quite nice. Mm-hmm. Okay, it's 7 p.m. in the UK already, so that's our session over for today. Thank you all for sending so many questions. We might have to do this weekly again if you continue this way. Thank you, Eva, for being here and answering all those questions. And I'm looking forward to seeing you all soon again. Let's see if it's in 1 or 2 weeks. I'll put an announcement on Twitter. Bye.